Okay, now let's begin.
Good afternoon, professors and researchers. It is my great honor to share my research content with you. My name is Li Yuanjing. Today, my research topic is mainly about the effect of changing PCM distribution on thermal performance of latent heat storage. My presentation would describe why should we use clean energy, the result of changing PCM distribution, and the explanation of corresponding phenomena. My presentation will contain 4 parts: the background, the numerical model, the results and discussions, and the last part, the conclusions. Now turn to the background. And there is one picture in this slide. The upper histogram describes the carbon dioxide emission, and the lower histogram is about the energy demand annual. From the changing trend, we could find that because the influence of the epidemic in 2020, the carbon dioxide emission and the demand of the energy decreased sharply. But in 2021, primary energy grew by 31 joules, the largest decrease in history, and more than reversing the sharp decline seen in 2020. Primary energy in 2021 was 8 joules, above 2019 levels. Emissions from energy rebounded strongly in 2021 back to around 2019 levels, and the increase in the carbon dioxide emission was mainly driven by economic activities. Because of the increase of carbon dioxide emissions, the global warming and other related problems has been worse and worse. In order to solve these problems, many countries had promised carbon neutrality and made policies to accomplish it. From picture, we could see that there was two countries which had finished the carbon neutrality, and many countries promised to finish this target by 2050. As far as China was concerned, all Chinese people tried their best to accomplish the carbon neutrality by 2030. One feasible method to decrease the carbon dioxide emission and alleviate the energy scarcity is to develop the renewable energy, such as the wind energy, the solar energy, and the hydropower. Among these renewable energies, the solar energy was one promising renewable energy because the solar energy is very abundant and its wide spectrum was suitable for many fields. But there is one drawback of the solar energy, that the solar energy is limited by the weather or the Earth's rotation. So, developing solar energy storage is one applied method, and the heat storage is divided into latent heat storage, sensible heat storage, and chemical energy storage. In this research, we chose latent heat storage thanks to its larger heat storage, isothermal characteristic during charging and discharging process. And Figure 3 describes the heat storage system. The upper picture shows the actual large-scale heat storage with molten salts, and it was one high-temperature heat storage system. The lower picture shows a small domestic heat storage system. It was used for daily heat water in our home. But there was one problem during the melting process. the melting performance was uneven. The PCM in the upper region melted faster than the PCM in the lower region, and the PCM in the lower region prolonged the full melting time. Additionally, the unevenness of the temperature in the high temperature heat storage would cause the thermal stress, which will affect the use of heat storage. In order to solve these problems, the gradient design of the phase heat or phase spaces were proposed, and the gradient parameters of the metal foam had been tested for melting performance, such as the gradient porosity and the gradient PPI. Except the above methods, this paper proposed that through changing the PCM distribution to improve the melting uniformity. And the second part is a numerical model. The figure A shows the physical model and its application area. The solar absorber collected the solar energy, and the heat is transferred by the heat transfer fluid to the heat storage and stored in the heat storage. The heat storage was consist of the proposed heat accumulator unit, and this paper selects one unit to analyze the thermal performance, and different proportions of radius, the upper radius and the lower radius, were designed, and their size was displayed in this table. The third part was the numerical calculation results and discussions. The first picture shows the full melting time of 10 cases, and the case 6 was the basic case, whose full melting time was 28,290 seconds. The best case was the case 3, having the full melting time of 17,210 seconds, saved the melting time by 39.17%. And as predicted before, the cases with more PCM in lower part all prolonged the full melting time. But we could conclude from the picture that if we increasing the PCM in the upper region excessively, it will prolong the full melting time too. And the sixth figure depicted the detailed changes of each case during the whole melting process, and the result showed that the melting fraction curves of the 10 cases coincided before about 500 seconds. This was mainly because at the beginning of the melting, only the PCM near the copper tube was heated up by conduction and melted. Therefore, the different distribution of PCM had no effect on the melting of PCM. So the melting fraction of each case was almost the same. So the curves coincided. From 500 to about 7,500 seconds, the melting fraction curves of 10 cases showed a great difference, among which case 2 melted fastest, case 6 melted slowest, and the difference between two cases was large. It should be noted that for case 1, case 2, and case 3, There was no decrease of the melting rate in the last melting process, but for other cases, there was a decrease of the melting rate in the last melting process. And the next was the melting interface. From this picture, we could conclude that the melting interfaces of different PCM distribution also had a significant difference. At 1000 seconds, for case 1 to case 4, there was small molten area in the area near the copper tube. Because under larger proportion, there was a area having little PCM, which needed a little heat to reach molten state. Additionally, for case 1 to case 4, at 8000 seconds, the liquid area near the copper tube was large, which was conducive for convection. And through changing the proportion of PCM, the last melting area changing from the lower region to the middle region. What's more, changing the proportion of the PCM would result in the change of average heat transfer resistance. This phenomenon could be interpreted that changing the proportion of PCM would change the distance between high temperature liquid PCM and the solid PCM. Because of the existence of natural convection, the high temperature liquid PCM always exist in the upper region of the heat storage, and the proportion with more PCM in the upper region decreases the distance. So it was conducive for high temperature liquid PCM transported by convection to transfer heat to solid PCM. And the first part was the conclusions. From this research, we could got 3 conclusions. The first conclusion was that, compared with the basic 1 case 6, the best one, case 3, with a full melting time of 17,210 seconds, had reduced by 39.17% through changing the proportion of PCM in the upper region and the lower region. The melting interfaces had changed. There was molten area in the lower region in case 1, case 2, case 3, case 4 in the melting beginning, and at 8000 seconds, the liquid PCM near the tube in case 1, case 2, case 3, case 4 was larger than other cases, which was conducive for natural convection. And the last melting area of these cases changed from the lower region to the middle region. And changing the proportion of the PCM would result in the change of average heat transfer resistance. For optimized cases, the thermal resistance decreased, so there was no decrease in the melting rate during melting process. Thank you for your attention and welcome your questions.
Oh, hello, Professor.
I thank you for your presentation. Yes, I think we have a question in the chat box. Can you see that? From Zhou Wei Chen.
Oh.
Would you like to take this question?
Okay.
thank you for your question. And your question was a tricky one when I was doing my research. As you have mentioned that for truncated coin, when the two-dimensional array was the same, the three-dimensional volume was not the same, which was different to the cylindrical storage. And in order to ensure that the PCM quality of all cases, in this research, we calculated the size of the heat storage tank with the same PCM in three-dimensional volume. And when we build our two-dimensional model, we all use these sizes under three-dimensional calculations. Professor, it's okay, Professor.
Okay, I think the question, yeah, I think you will answer the question. So thank you so much.